So you can just put swabat, you don't have to put swag. So chapter 11, there's only 3 sections in chapter 11, but each section actually has quite a bit of information in each piece of it. So we're going to be talking about parametric curves, vectors, and polar curves. So you guys should have seen polar. You guys should have seen polar coordinates last year, hopefully.
Probably did, but
Okay.
it's been a while. Yeah,
also-
that class was.
So we're going to review some of the basics with polars, because probably you've forgotten. You've only seen it once in your math career, whereas, you know, the Algebra 1 stuff, now you have it beaten into your head because it's been 6 or 7 years in a row that you've been doing Algebra 1. So we're going to work with parametric curves, and we're going to find the derivative of a parametric curve and find the arc length of a parametric curve today. So do you guys know what I mean when I say a parametric curve?
It's a curve that's like
So no idea what parametric means?
Nope.
Okay.
It's like a disabled metric.
Oh.
So a parametric curve is where you have x equal to something with t's in it, and y equal to something with t's in it. It's a way to take a relation and work with it a little bit easier. We like functions to work with. What's the difference between a function and a relation?
Functions like equal.
Function or relationships don't.
Think of it graphically. Which one is a function, which one is a relation?
Line test.
Function passes the vertical line test. For every x value, there is only one y value. Whereas a relation, if I pick this x value, there's 2 y values. So relations are harder for us to work with, but if we split it up and work with it in a parametric mode, then each piece of the parametric function itself will be a relation. So if we have a relation x equals y squared, what does that look like? Sideways, except it'd be centered. X equals y squared, and I'm going to write this as a parametric function. I'm going to say x of t equals something, y of t equals something. And they both then have to have t's involved. So most often we take the more complicated piece and just replace that letter with t. Yeah. So what's the more complicated piece of this? Y squared. I'm going to replace the letter y with t. I'm going to say y of t is t. I'm defining y to equal t. Well, what would that mean for x of t?
Squared.
It's t squared. So now each of these would be its own independent, well, not independent, each of these would be considered a function on its own. Together they would still make the picture you see up there. So if we were going to graph this parametrically, we're actually picking t values. So they call them t steps. In your graphing calculator, it'll say t steps. It's the t values you're picking. And picking those t values will then give you an x and a y value that you could graph. So if we were going to graph this, we would need 3 columns to our table. So I can pick whatever I want for t. What do we want to pick for t? 1, 3. 0 is probably a good one. What kind of numbers are we missing?
Negative.
Negative numbers, so -1. Obviously this is not in any order since we randomly picked numbers. Usually we'd put them in order. So now I can find x and y coordinates that I could then go graph by plugging them into our equation. X of t, if I plug in 1, 1 squared, which is 1. Y of t is nice because if I plug in 1, it's the same thing. If I plug in 3, x of t, 9, y would still be 3. 0 would give me both zeros, and -1 would give me 1 and -1. So now we have a whole bunch of coordinates we could go plot on the xy plane. Sorry, I should have left a little more room. So if I make my graph, I can now plot these individual points. 1, 1, 9, 3, 0, 0, and 1, -1. And we do get our sideways parabola. So let me look again what the instructions for this example were. I know what I want to do, but I want to see how the book is going to state the instructions. Like I said, I didn't have time to type this up, so I didn't get to make the changes I normally like to make. So the instructions will say eliminate, I can spell, eliminate the parameter, to find an equation, parameter being the t's. So basically they're saying we went one direction. We took x equals y squared and made it into a parametric function. They just want us to take our parametric function and go back to just a function with x and y. Now if any of them just ever equal t, those are the easiest. If y equals t, I can just replace t with y. Something like this, we have to get a little more creative. And it's something that will just come with practice. X equals cosine t and y equals sine t. This is actually a commonly used parametric function that if you're working with them a lot, you'd be like, oh, I know what this is. This is a circle. Okay. These two together would make a circle. But we have to be a little creative in order to rewrite this so that we can replace x and replace y. So we need to use something that's always true, so some sort of formula, that involves both cosine and sine, so that I could replace the cosine t with x and I could replace the sine t with y. So we want something that's always true. So you guys should still have those formula sheets that I handed out at the very beginning of the year with the trig formulas. not slackerish?
Mine are in my
Okay.
other folder.
Eliana and Ben are only non-slackerish, and Eliana's less non-slackerish because she already turned to it. Okay, so we're looking for a trig formula that involves both cosine and sine. And it can involve numbers, but it can't involve other functions, or else we can't do our replacement.
Sine squared. No.
So sine squared plus cosine squared. What do we know about sine squared? And I'm going to use t because that's our whole point, is to be able to replace sine t. What do we know about sine squared plus cosine squared? Equals 1. So, what do we know about sine t? It equals y. So I can replace sine t. And remember, this is really sine t squared. But with our trig functions, we write the squared after the sine before the t.
So it's just y squared plus x squared.
Which is the equation for a circle.
Circle.
So x equals cosine and y equals sine is our way, at least that's our way to write a circle of radius 1. Bless you.
You don't have to get y on by itself when you do these.
Nope. That's the whole purpose, is working with parametric, is to work with things where y is either not easy to get alone, or like this one, if we got y alone, we'd end up with 2 functions, because we'd have to use a function that says y equals positive square root of 1 minus x squared, and y equals negative square root of 1 minus x squared. So when we differentiate a parametric function, differentiating a parametric function is a little bit different than differentiating normally, because we have an x of t and we have a y of t. So to find the derivative, we have to take the derivative of the y piece. This dyt is that y of t, so y prime of t. Dx dt is x prime of t, and we divide them. And this is something I still don't really know why. I just know it's what you do. To find the second derivative, it gets even more complicated. We take the derivative of, see, parametrics in me, the second derivative is the one that's always hard to remember. Because when they say dy prime dt, so dy d prime dt is the derivative of this thing you found first. So to find the second derivative, dy prime dt is actually the derivative of this entire thing. Which means if you're dividing, you're probably going to have to do quotient rule to find this piece. And then we're going to divide by dx dt again. Again, not 100% sure why, but I know that's how you do it. Okay, so let's practice finding the derivative. Finding the first and the second derivatives of this function. So the first derivative's easy. Take the derivative of each piece, stack it. First derivative, not a problem. I can find dx dt very easily. What's the derivative of dx dt? Remember, derivative of x with respect to t is just saying t is our variable that we're taking the derivative of.
So it's just 2t.
2t. Just 2t. And I can find dy dt easily.
Get it. You get it.
Okay. What's our derivative of dy dt? 2 cosine t. So the derivative of y with respect to x. Ooh, now I get why the first one is this way. Let me show you really quick. If I take dy dt and divide it by dx dt, fraction-wise, what do I have to do with the second piece? Flip it. So dy dt times dt dx is dy dx. So now we know why we divide the two pieces. So dy dx would be 2 cosine t over 2t. We just divide the y, the dy dt by dx dt, which we can clean up a little bit. What's going to happen when we clean it up? So these cancel. So then it's the second derivative that's weird. The second, yes.
Okay.
The second derivative is going to use this dx dt piece we've already found. The second derivative we already know, nope, d squared y, has a delay now, dx squared. We already know the entire thing will be divided by 2t. We just have to figure out that numerator. And that numerator is the derivative of this we found first. So we have to find the derivative of this entire thing. Close.
We can just bring it
You could bring it to the top and do product rule. Quotient rule. So low d high minus high d low. Yep, so t d high is negative sine t minus high d low cosine t times 1 all over low low, so all over t squared. So now we have to put this over the 2t. We have, and I'm going to clean it up a little bit, negative t sine t minus cosine t all over t squared. So we do have to do some fractional division. If it's all over 2t, where is that 2t going to end up, the top or the bottom? If we're dividing by 2t, it actually ends up in the bottom. This is why I actually always write out my fraction over a fraction old school. Because I can never figure it out unless I write this old school and say, okay, now I multiply by 1 over, it's going to go on the bottom. So then our final answer would be negative t sine t minus cosine t over 2t to the third. That would be the second derivative. So first derivative, super easy. Second derivative, we have to remember, we're going to be tempted just to do either the second derivative of those pieces or the second derivative of just the entire thing. It's a combination of the first derivative of a piece and the second derivative of the entire thing. So I want you guys to try differentiating a problem. I want you to find both the first and the second derivative. Oh, wait, I want to add a page. Okay, so as I predicted, the first part, not hard. No, x prime, I should say dx dt. So first derivative, none of you guys had trouble with. Stuff can cancel though. So we just have square root of 3. Second derivative, we need the derivative of this piece. So what is the derivative of square root 3?
0.
0. So the second derivative over the negative sine t again. So the negative sine t was used twice. In this case, it doesn't matter because what's 0 divided by negative sine t?
0.
0. So the second derivative is just 0. So we're going to learn just one more thing we can do with parametric curves today. And that is to find the arc length. Anyone remember the arc length formula? This was in like unit 8 or chapter 8. We wrote it down as well. It was based off
It's
distance formula. We have distance formula.
if you have and then you have
So if we're doing this Newton-wise, no, Leibniz-wise, derivative of x would be dx over dx. Derivative of y would be dy over dx. So derivative of x is dx over dx. What is that really? 1. Hopefully I'm remembering that correctly. Let's look it up to make sure. So you should have made a note card for it as well. Look in your note cards and see if you can find your arc length note card. Or, because 7 was volumes. No, 7 also, I think 7 had arc length. So you could also look in your,
I've done a lot of flashcards for this class.
there's a lot to remember.
Where did you get the negative sine t?
This is used both times. Again, not sure why, at least on the second one. The first one, we kind of saw the sense of it in the division. The second one, don't know why. Just know that it is. Did you find it?
I didn't find it.
Did we not make one?
I don't remember.
Chris's.
So,
We should have made one.
Pamela, did you have a lot of secrets?
I was trying to hold that open. I cannot find.
I know we've done Earthling.
Is that supposed to be after the?
Yeah, it's at the end. I just ran out of room.
Yeah. It was really dumb. But when we had the salt water on the bottom of our thing, no, yeah, it broke. Sorry.
Okay, so you already have the arc length written down on a note card. This one's all about using the formula. So it's impossible to do without the formula. And it says from T1 to T2. So they've got to tell you an interval somehow. They have to tell you where to start and where to end. This particular one is called an astrid, cosine cubed and sine cubed. When it was just plain cosine and plain sine, it was a circle. When it's cubed, it kind of curved in the pieces of the circle, like you flipped each quarter of the circle in. But this one's all about using the formula. So we need dx dt and we need dy dt, which is chain rule. This is cosine t all to the third. We've got to do derivative of the outside, evaluate it at the inside, times the derivative of the inside. So I want you guys to find these two derivatives first on your own, just to make sure we remember how to do chain rule.
Oh, yeah.
Okay, so I checked everyone's derivatives. Cleaned up, they would look like this. So now we literally just plug this into the formula. Arc length isn't usually super difficult because it's a plug into the formula and then plug it into your calculator because we cannot integrate it. So we have the integral. What are our bounds? 0 to 2 pi, because that's what they told us for t. 0 to 2 pi of the square root of negative 3 cosine squared t sine squared, or sine t, all squared, plus 3 sine squared t cosine t, all squared. That was dx dt squared plus dy dt squared. And then it's literally a plug it into your calculator at this point because there is no way for us to integrate. Well, okay, it looks like they made this one in such a way that I could technically integrate it. But-
3.2.
Yeah, that is the question. Do we really want to?
I'm feeling like a mathematician today. Let's go.
Birthdays.
Yeah, they did technically make this one integratable by hand.
No ones, no ones.
Just use a calculator. Bless you. Yeah, this one is a lot to type in. So, we put this entire thing in, we get 6. So for your homework, which you're going to have some time in class to work on your homework today, page 541.
Five problems.
7 through 15 on. And season through 35. And we will be spending 2 days on this first parametric section.
Oh no.
So how are you doing the voting for the art